Here's a video for the quadratic formula. So in our previous lesson, we learned that our discriminant can tell us how many and what types of roots or solutions when f of x equals 0 a quadratic has. The quadratic formula will actually tell us what those roots are. So we know that we can also find roots by factoring if the quadratic is factorable. However, not all quadratics are factorable. So this is the quadratic formula. So when we have a quadratic written in standard form, which is ax squared plus bx plus c, we can determine the roots using the quadratic formula. So the roots are going to be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If you look, the part underneath the radical is our discriminant. Well, we know when our discriminant is positive, we end up with two distinct real solutions. And those solutions would be negative b plus or minus the square root of the discriminant over 2 times a. We know that if b squared minus 4ac is equal to 0, we end up with just one solution, or I guess two identical real solutions, aka one x-intercept, because this would end up being negative b plus or minus the square root of 0, which is just going to be negative b over 2a. And then lastly, our third solution, or our third type of solution, was when b squared minus 4ac was a negative number, we end up with two distinct complex or imaginary solutions. So what we're going to learn today is b squared minus 4ac, when that's negative, how to simplify that negative radical. All right, so let's take a look at this first example. So first thing we're going to do is we're going to identify a, b, and c. So a is the coefficient of our x squared term. B is the coefficient of our x term, and then C is our constant term. So A is going to be 2, B is going to be 7, and C is going to be negative 2. And then we're going to plug it into our formula. So we have x equals negative b, so that's going to be negative in parentheses 7, plus or minus the square root of b squared, so 7 squared minus 4 times a times c. All over 2 times a. So all we did was plugged in our a, b, c into the quadratic formula. Remember, using parentheses every time we plug something in. And then we're just going to simplify it in parts. So the first part we're going to simplify is this negative b part. So it's just negative 7. So we end up with just negative 7. Plus minus the square root. Next thing we're going to do is we're going to simplify the part underneath the radical. So we're going to do 7 squared minus 4 times 2 times negative 2. I suggest just putting that in our calculator. So plugging b squared minus 4ac into our calculator. So here it is. This is the discriminant. We get 65. So knowing what we learned yesterday, we know that when our discriminant is positive, we end up with two distinct real solutions. So using the quadratic formula, we're going to determine what those solutions are. So we have a square root of 65 that goes underneath the radical. So square root of 65. And then in the denominator, we just do 2 times 2, which is going to be 4. So at this point, we have to see if we can simplify it further. So then we're going to look at our radical, and we're going to see if we can simplify this any further. Well, when simplifying radicals, remember we want to list out our factors of our radicals. So that's 1 and 65. The next number that goes in is 5 and 13, and those are the only factors. So looking at these, the only perfect square that we see is 1, and if the only perfect square is 1, that means our radical cannot be simplified. Which means that this is our fully simplified answer. So this is two distinct real solutions. My first solution, exact solution, is negative 7 plus the square root of 65 over 4. And then we also have x equals negative 7 minus square root of 65 over 4. So these are my exact answers. However, if we want to get an idea of what this would look like graphically, well, I know that this is a graph that's concave up, and we know it's going to intersect our x-axis twice. It's hard to figure out where this falls on the x-axis. So let's put this in our calculator and get a couple approximate answers so we can get a better idea of where our x-intercepts are on our graph. So I'm going to put these in our calculator. So my first approximate answer, I have 0.27. So it's approximately 0.27. And for my second solution, it's basically going to be the same thing, except it's going to be -7 minus square root of 65 over 4, and I get negative 3.77. So now we can get a better idea that my x-intercepts are somewhere around here, and we can kind of see kind of what our graph looks like. So these are my approximate answers. All right, so now let's take a look at example 2, which is partially done here. So here's my equation, f of x equals 2x squared minus 6x plus 3. First thing we identify is a, b, and c. So a is 2, b is -6, and c is +3. And then we plug it into the quadratic formula. So we have negative b is -6, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. When we simplify this down, the -6, those two negatives turn into a positive. And then when we plug in our discriminant, -6 squared minus 4 times 2 times 3, you should get 12. And then lastly, in our denominator, 2 times 2 is 4. So based off of our discriminant, we know that this is positive, which means we end up with two distinct real solutions. But we're going to see if we can simplify this further. So just like we did before, we're going to take our square root, and we're going to see if we can simplify that. Well, my factors of 12 are 1 and 12, 2 and 6, and 3 and 4. And scanning our list, we know that 4 is a perfect square. So we can rewrite the square root of 12 as the square root of 4 times the square root of 3. So you want to rewrite it as a perfect square and another number. So the reason we do that is because the square root of 4 is 2, and then we would leave the square root of 3 underneath the radical. So that's essentially what we did, is we took out a perfect square from here. So we know that square root of 12 is equivalent to 2 times the square root of 3, which means we can rewrite our solution as 6 plus or minus 2 square root of 3 over 4, since we know that the square root of 12 is equal to 2 times the square root of 3. So from this point, we need to actually see if we can simplify it further. So if you can simplify the radical, then you have to take a look at your numbers on the outside. If these are all divisible by the same thing, then it can be simplified further. So in this step, we were simplifying the radical. But as we can see, all the numbers on the outside are actually divisible by 2, which means we can simplify this further. 6 divided by 2 is 3. 2 divided by 2 is 1. So it just basically cancels out. And then we just left with the square root of 3. And our denominator, 4 divided by 2 is 2. So here's our answer fully simplified. I have my two answers, x equals 3 plus the square root of 3 over 2. And then we have x equals 3 minus the square root of 3 over 2. So these are my exact answers. And what we're going to do is we're going to put those in our calculator to get my approximate. So as we can see, when we put these in our calculator, we end up with x equals about 2.37, and my other solution is x is about 0.63. All right, so now let's take a look at example number 3. So here's my example, f of x equals x squared plus 2x minus 24. We're going to identify a, b, and c. Remember, when there's no number in front of x, that number is actually 1. B is 2, c is -24, plugging it into the quadratic formula, so negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. And when we simplify this down, -2 in front becomes just -2 plus or minus. Our discriminant, b squared minus 4 times a times c, that simplifies to 100, and then 2 in the denominator. So again, based off our discriminant, we know we have two distinct real solutions. So now we're going to see if we can simplify this further. So we look at our radical, and 100 is actually a perfect square. The square root of 100 is actually 10. So this actually is going to be simplified to -2 plus or minus 10 over 2. Well, at this point, we can kind of just break it apart into two different equations, or two different expressions. -2 plus 10 over 2, and -2 minus 10 over 2. But since these are all integers, we can actually go ahead and add them and simplify. So -2 plus 10 is 8 over 2, which simplifies down to just a 4. And then we have -2 minus 10, which is -12, over 2, which gives me negative 6. So my two solutions in this case are just exact solutions. I have 4, x equals 4, and x equals negative 6. So you end up with two rational solutions, and actually when your solutions are rational like this, that essentially tells me that this quadratic is factorable. We could have solved this by factoring. We could have factored this into x minus 4 and x plus 6. And then what we could have done is solve by factoring using zero product property. The number that makes x 0 in this case would be 4. That's our first solution. The number that makes x 0 in this case would be negative 6. That's our second solution. So a rule of thumb kind of when we're trying to determine if a quadratic is factorable, if your discriminant is actually a perfect square, that's essentially going to tell you that your roots are going to be rational numbers, which means that they were factorable. Your quadratic was factorable, and you could solve it by factoring, as well as solving it by using the quadratic formula like we did in this example. All right, so now let's take a look at example number 4. So again, here's my quadratic, 2x squared plus x plus 2. A is 2, b is 1, c is 2. Plugging our quadratic in here. I actually see a couple mistakes here that I need to fix. These should all be positive 1. Okay, so plugging our quadratic in here, we get x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this first parentheses is going to simplify to a negative 1 because it's negative positive 1 plus or minus 1 squared minus 4 times 2 times 2. We end up with negative 15, and then 2 times 2 is 4. So now we need to look and see if we can simplify this radical. Well, this is the first case where our discriminant is negative, and as we learned in a previous lesson, when our discriminant is negative, we end up with two distinct complex or imaginary solutions. So now we need to kind of learn a little bit about imaginary numbers. So just so you can visually see what's going on here, again, I need to fix a couple things here. Okay, this is the graph of our quadratic, and as we can see, we don't intersect the x-axis at all, which means that our answers are not going to be real solutions. Our roots are not going to be real, they're going to be imaginary. So they're intersecting some imaginary axis, and we need to know about imaginary numbers in order to be able to further simplify this quadratic. So why imaginary numbers? It allows us to find solutions to equations that do not have real number solutions, such as the one that we were working with. So here are some different number systems, and they're all kind of the number systems that we've learned all fall under real numbers. So natural numbers are numbers like 1, 2, 3, and 4. Then we have whole numbers, which adds in 0. We have integers, which we kind of created negative numbers. And then we have rational numbers, such as fractions or decimals. And then we have real numbers. And then kind of a separate category, we have irrational numbers, such as like the square root of 2. But then there's a whole nother set of numbers called imaginary numbers, which is, this is kind of blurry, kind of hard to see. These are imaginary numbers. So what we need to learn is that the square root of negative 1 can be simplified down into I. It is an imaginary unit. So we've now introduced this whole new concept of a new set of numbers, which are square roots of negative numbers. So we can simplify square root of negative 1 to I. So for example, when we're simplifying radicals such as these, well, we know that we can, 100 is a perfect square, but we can actually rewrite this as square root of negative 1 times square root of 100. Since negative 1 times 100 is negative 100. Well, we know square root of 100 is just 10. And we now know that the square root of negative 1 is equal to I. So the square root of negative 100 is actually equal to 10I. We could do the same thing with radicals that aren't perfect squares. We can rewrite square root of 65 as the square root of negative 1 times the square root of 65. And we now know that the square root of negative 1 is I. And as we saw in that previous example, square root of 65 cannot be simplified. So we can rewrite square root of negative 65 as I times the square root of 65. And then let's take a look at an example where we have a radical that can be simplified. So I can rewrite this as square root of negative 1 times the square root of 8. And we can actually rewrite the square root of 8 as the square root of 4 times the square root of 2. Oops. Sorry, so square root of negative 1 times square root of 4 times square root of 2. So we can see negative 1 times 4 is negative 4, negative 4 times 2 is negative 8, and this could fully be simplified to square root of negative 1 is I, square root of 4 is 2, and then square root of 2 can't be simplified to square root of 2. So we can actually rewrite the square root of negative 8 as 2I times the square root of 2. So it's kind of convention, if there's no square roots, to write it like 10I, the same way you would write like 10x. If there is a square root, you should put the I first and then the square root of 65, just because if you write it after, it kind of looks like the I is underneath the square root. And then same thing here, we would write 2I times the square root of 2, although really the order of how you write it doesn't matter, it's just kind of convention to write it this way. So now knowing what we know, we can simplify this further. The square root of negative 15 can be written as square root of negative 1 times square root of 15. Well, 15, my only factors of 15 are 1 and 15 and 3 and 5. So since there's no perfect squares, that means square root of 15 can't be simplified. But we can simplify square root of negative 1 as I times the square root of 15. So now our final answer, it's going to be x equals negative 1 plus or minus I square root of 15 over 4. So we do need to make sure we simplify, if we have a negative square root, that we pull out an I for it to be fully simplified. So now I have two answers. It's going to be negative 1 plus I square root of 15 over 4. And then we have x equals negative 1 minus I times the square root of 15 over 4. For these ones, we're not going to get approximate answers because our calculator can't handle imaginary numbers and it won't give us an approximate answer. So we're only going to have exact answers in this case. All right, so now let's take a look at our homework problems. So first thing I'm going to do is I'm going to identify A, B, and C. So here's A, here's B, and here's C. And now I'm going to plug it into my formula. So anytime we're plugging in something, I suggest using parentheses. Okay, so it's negative B, so B is negative 4, plus or minus the square root of B squared minus 4 times A times C, all over 2 times A. So make sure when we plug in our number that the sign goes with the number. So B is negative 4, so when we plug it in inside of parentheses, it should be a negative 4. Okay, so now we're just going to simplify it in parts. So first part we're going to simplify is the negative B part. So the negative 4 becomes a positive 4. Second thing we're going to simplify is this radical. So we're going to go ahead and put that in our calculator. So when we plug that in our calculator, we get 100 for the discriminant, which tells me that we have two distinct real solutions. And our denominator, 2 times 3 is 6. So now we're going to simplify it further. So this is like the example from the notes. Square root of 100, that is a perfect square, and that simplifies down to 10. So I have 4 plus or minus 10 over 6. So we are going to end up with two rational expressions, two rational numbers, 4 plus 10 over 6, and 4 minus 10 over 6. So 4 plus 10 is 14 over 6, and then 4 minus 10 is negative 6 over 6. So this ends up simplifying to negative 1, and this ends up simplifying to 7 over 3. So my two solutions are 7 over 3, and x equals negative 1. All right, looking at number 4. So A in this case is 1, B is equal to 4, and C is equal to negative 4. So now I'm just going to plug it in. So negative B plus or minus the square root of B squared minus 4 times A times C, all over 2 times A. All right, now we're going to simplify it in parts. So out front, we just have a negative 4. And now we're going to plug our discriminant into our calculator. All right, so when we plug in our discriminant, 4 squared minus 4 times 1 times negative 4, we get 32. So plus or minus 32, and 2 times 1 in the denominator is 2. So now we need to see if we can simplify our radical. So factors of 32, 1 and 32, 2 and 16, 4 and 8, and then that's it. So scanning our list, the largest perfect square I see is 16. So we're going to rewrite this as the square root of 16 times the square root of 2, since 16 is our perfect square. And then the square root of 16 is just 4. So we end up with 4 times the square root of 2, which we're going to swap out here. So negative 4 plus or minus 4 root 2 over 2. Then we need to take a look. Anytime you simplify your radical, you should look at the numbers on the outside, see if you can simplify further. Well, all of these numbers are divisible by 2, or you can think that we can do negative 4 divided by 2 and 4 divided by 2. So if we do that, we end up with negative 4 divided by 2 is negative 2. 4 divided by 2 is 2. So you end up with negative 2 plus or minus 2 root 2. So my two exact solutions is negative 2 plus 2 root 2 and negative 2 minus 2 root 2. And then if we put those in our calculator, we can get our approximate solutions. So negative 2 plus 2 root 2 gives us 0.83, approximately 0.83. And then negative 2 minus 2 root 2 gives me approximately negative 4.83. Again, the reason for getting the approximate answers is then we can kind of get a visual idea of where our x-intercepts are. All right, now let's take a look at number 6. So we're going to identify A, B, and C. So A is 4, B is negative 5, and C is 4. Now we're going to plug into our formula. So negative B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. So now just simplify it in parts. So the negative B, negative 5 becomes positive 5. Now we're going to put the discriminant in our calculator. So when we put that in our calculator, we get negative 39. And then 2 times 4 in the denominator is just 8. So we see that the value of the discriminant here is negative, which means we know we're going to end up with two distinct complex or imaginary solutions. So we're going to see if we can simplify a square root of 39. Well, we know that that's a negative, so I can rewrite it as square root of negative 1 times square root of 39. And then if we list out our factors of 39, well, we have 1 and 39. And then we have 3 and 13. But I believe those are the only factors of 39, and none of these are perfect squares, which means the only way that we can simplify square root of negative 39 is if we just simplify the negative, which we know this becomes I, so this ends up being I times the square root of 39. So fully simplified, our answer is going to be 5 plus or minus I square root of 39 over 8. So you can just keep it like that if you want. I know my answer key kind of has it written like that. I do like to write it as two separate equations just because it kind of emphasizes that there's two distinct solutions rather than two identical solutions. So 5 plus I root 39 over 8, and then 5 minus I root 39 over 8.